Howdy, howdy. This is Mr. Potter. Today we're going to go over the 2018 free response questions for the AP Calculus BC exam that was given earlier this week. So let's go ahead and start with problem number one. Number one says that people enter a line for an escalator at a rate modeled by the function r, given by r of t equals 44 times t over 100 cubed times 1 minus t over 300 to the seventh for values of t between 0 and 300 inclusive, and 0 for t is greater than 300, where r of t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 persons per second. There are 20 people in line at t equals 0, and part A starts with how many people enter the line for the escalator during the time interval 0 less than t less than 300. So keep in mind that this is a rate, which means if I want to know the number of people, then what I'm going to have to do is take the integral from 0 to 300 of this function, r of t dt. So I'm going to have to take the integral from 0 to 300 of 44 times t over 100 cubed times 1 minus t over 300 to the seventh dt. So we're going to go ahead and do this. So I'm going to do F3 for calculator. We're going to integrate, and I want to integrate 44 times t divided by 100. I need parentheses there. Raised to the third times, and open parentheses again, 1 minus t over 300, close to the seventh power. So that's my function. I want to integrate with respect to t from 0 to 300 and figure out what the result of that is. And we get 270. So this is 270 people that have gotten in line. These are 270 people that are getting into line for this escalator over this first 5-minute period, the 300 seconds. For part B, it says during the time interval 0 less than t less than 300, there are always people in line for the escalator. How many people are in line at time t equals 300? Well, keep in mind that I've got r of t, which is defined piecewise. That's at 44 times fractions. And keep in mind that this is on, but I also have people getting off the line, and this is also a rate. And that rate is a constant 0.7. So if I want to figure out the total people on, or the total people in line, I should say, that's going to be equal to the integral of the rate coming in minus the rate coming out. And again, I'm integrating from 0 to 300. So when I do this calculation, I'm going to go do my exact same equation. The only thing that's going to be different is my function's going to have a minus 0.7 in it. And now when I try and do that integral, I end up with 60 people. Okay, so total people in minus total people out over that time, because these are rates. For part C, it says for t greater than 300, what's the first time t that there are no people in line for the escalator? So for t greater than 300, r of t is 0, and s of t is still 0.7. So I want to integrate from 300 to some unknown t value, and I want to integrate 0 minus 0.7 dt. Well, this is going to be 0.7 t, which I'm evaluating from 300 to t, and I want to know when this result is going to use up all of these 60 people that we had in line. So I want to know when this is equal to 60. So I've got 0.7 t minus 300 times 0.7, and I want to know when that's equal to 60. And of course, I don't trust myself to try and, I don't want to factor, I want to solve. I don't trust myself to do this in my head or even do it on paper. I'm going to solve 0.7 t minus 300 times 0.7 equals 60, and I want to solve for t. And when I do that, I end up with t equals 385.714 seconds. So that's going to be the time that there's now no one on the escalator. It just takes 85 seconds for everyone to clear that off. Okay, on to part D. On part D, it says for 0 less than or equal to t less than or equal to 300, at what time t is the number of people in line a minimum? And it says to the nearest whole number, find the number of people in line at the time, justify your answer. Keep in mind that we know extrema occur at critical points and boundary points. And I know that my boundary points are going to be at 0 and at 300, so these are values that I'm going to have to determine. But then I also need to know extrema. And extrema occur when the derivative is equal to 0 or undefined. So for us, our derivative function is really that r of t minus s of t that we were dealing with earlier. So it's going to be that 44 times t over 100 cubed times 1 minus t over 300 to the seventh minus 0.7. And I want to know when this is equal to 0, and I don't have to worry about undefined because we're not dealing with fractions here. So we're going to go ahead and type this in. We're going to do another solve. And we're going to solve for 44 times t over 100 cubed times 1 minus t over 300 raised to the 7th. And that's going to be minus 0.7. And I want to solve this for t. Now I will tell you that this will take a bit of time. Wait, what's wrong with this? First argument of a solve or c-solve must be an equation or inequality. I forgot the equals 0. I need to take care of that real quick. Equals 0, because I'm looking for a critical point. Now, by the way, we've already done these answers over here, because here I'm doing the integral from 0 to 0 for this. And keep in mind that the initial people in line was 20 people. And I've already done the integral from 0 to 300 because that was part B. And on part B, that was 60 people. So I know that the number of people at time 0 is 20 people. I know that the number of people at time 300 is 60 people. So all I need to do is figure out the critical points of this expression. And of course it is still calculating. It will take a while to do that, and that's okay. I've already done this though, and I'm going to tell you that they occur at 33.0133 seconds, and t equals 166.575 seconds. Oh look, it's already got that up, great. So now what I need to do is I need to figure out what n of 33.0133 is, and what n, the number of people at 166.575. And that means I need to evaluate these integrals again. So let me see if I can go up to the integral that I had up here and just change the limit, because I only want to, in this case, I only want to go up to 33.0133. What did I do wrong there? Syntax. I'm integrating with respect to t from 0 to 33.0133. I think I've got too many parentheses here. That's what it is. And we end up with negative 16.1966 people. Now, this has a meaning to us in the context of the problem. How can I have negative 16 people? Well, it must mean that the rate of people coming off the elevator was faster than the rate of people coming on, and at some point the elevator was empty. So this is really going to be 0 people. I'm going to need to do the exact same thing with 166.575. And this is 138.07. So in other words, this ends up being my minimum. And so I have a minimum of 0 people at t equals 33.0133 seconds. Now, it didn't ask where the maximum was, but my maximum is occurring at 166.575. And of course, these 20 and 60, those are just boundary points, so those are values in between. What's interesting to note is that this function looks an awful lot like a logistic function where I've got a constant times some population times 1 minus my population. And so I can imagine my population being this t over 300, so I'm expecting a curve that's going to do something like this. My rate's going to start off pretty low, and then it's going to come out high, and then it's going to flatten off again. And no coincidence, that just happens to look like an escalator. So that's problem number 1. And on to problem 2. Problem 2 says researchers on a boat are investigating plankton cells in a sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter is modeled by P of h equals 0.2 h squared e to the negative 0.0025 h squared for 0 less than h less than 30 inclusive, and is modeled by f of h equals h is greater than 30. This continuous function is not explicitly given. They want us to find p prime of 25. So they're asking us to find the derivative of this function. So I'm going to do differentiate, and I'm going to type in my function, which is 0.2 h squared times e to the negative 0.0025 h squared. And I want to integrate this with respect to h, and I want to do this at h equals 25. And so when I do this, I find out that p prime of 25 is equal to the integral, or not, excuse me, the derivative of that. So it's the derivative of p of h at h equals 25, which is negative 1.17906. And keep in mind that this is a rate of change, so this is going to be million plankton per cubic meter per meter. In other words, the density of plankton is decreasing at negative 1.179 million plankton per cubic meter each meter at h equals 25 meters. So that's my justification, that's my explanation, and that's part A. So now moving on to part B. On part B it says, consider a vertical column of water in the sea with horizontal cross-section of constant area 3 square meters. To the nearest million, how many plankton cells are in this column of water? So I have some column of water. I have no idea what the shape is, but I know that if I take any cross-section of this, I know that the area is 3. And I know that if I ever want to find volume, all I have to do is integrate area with respect to some length. And I know that in this case, I want my depth to go from 0 to 30 meters. So if this is volume, and I know the density, then the number of plankton is going to equal the volume times the density. The only thing is that my density is actually a function of h. So I need to make sure that I'm going to integrate from 0 to 30 my area function, which is 3, times my density function, which is 0.2 times h squared times e to the negative 0.0025 h squared dh. So I'm going to do that integration. So we're going to do calculus 2, excuse me. Stop it. Calculus 2. We're going to integrate 3 times 0.2 times h squared times e to the negative 0.0025 h squared. And I want to integrate this with respect to h from 0 to 30. and we end up with 1,675.41 million plankton. Of course, they're asking us to do this to the nearest million, so we'll go ahead and take care of that. That's how many plankton it is to the nearest million, 1,675. On to part C. Part C says there is a function u such that 0 is less than f of h is less than u of h for all h greater than 30, and the integral from 30 to infinity u of h dh is equal to 105. The column of water in part B is k meters deep where k is greater than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column, and explain why the number of plankton cells is less than or equal to 200 million. Well, if I'm trying to find the number of plankton, then what's going to happen is I'm going to be doing the integral from 0 to k of this f of h. But I know that this happens to be less than or equal to the integral from 0 to infinity of f of h dh, because my plankton have to be, if I go deeper, I have to have more plankton. That's just a rule of the ocean. And I know that this is equal to the integral from 0 to 30 of f of h dh plus the integral from 30 to infinity of f of h dh. Because if I have a big interval, I can always split it up into two smaller intervals. And I happen to know that this is less than or equal to the integral of this, which is exactly the same, plus the integral from 30 to infinity of u of h dh. But I know that this is 105. And I know from the previous problem that this was how much? 1,675. And I know that this is less than 2,000 millions. So that's how I can justify this. This is why I can explain that that's going to be less than 200 million. So I've written an expression here using one or more integrals that gives us the plankton cells in millions. Now, if I wanted to, I could make this slightly different and write this as the integral from 0 to 30 of f of h dh plus 105. And I could say that that's going to be strictly less than, because I know this is true. Not strictly less than, just less than or equal to. So that's part C. Let's take a look at part D. On part D, it says the boat is moving on the surface of the sea at time t equals 0. The position of the boat is given by this parametric expression x of t, y, and t, where x prime is given by 662 sine of 5t, and y prime is given by 880 cosine 6t. Time is measured in hours, x and t and y of t are measured in meters. They're asking for the total distance, and I know that the total distance between points A and B can be written as the square root of x prime squared plus y prime squared dt. So I'm going to be integrating from 0 to 1, the square root of, this is going to be 662 times the sine of 5t that I'm going to be squaring. And this is going to be 880 times the cosine of 6t that I'm going to be squaring. And I'm going to be integrating this with respect to t. So I'm going to be integrating the square root of, so I'm going to take this whole thing and raise it to the 0.5 power. And inside here, I'm going to take something and square it. And the thing I'm going to square is going to be 662 times the sine of 5t. And I'm going to add something squared. And the something squared that I'm going to add is the 880 times the cosine of 6t. And I need to make sure I'm closing parentheses as I go. So this needs a closed parentheses there to make sure that that whole expression is being squared. And this 880 cosine of 6t also needs a closing then close to square, and then that whole thing's being square rooted. And I want to integrate that with respect to t from 0 to 1. And while we're waiting, and so we end up with 757.456. And because they tell us x and t and y of t are measured in meters, that's the units that we're using. Okay, so there is problem number 2. And so that's our calculator section. So let's go ahead and get rid of our calculator, and we will move on to the rest of our test. And on to problem 3. Problem 3 says the graph of the continuous function g, the derivative of the function of f, is shown above. The function g is piecewise linear for -5 less than or equal to x less than 3, and g of x equals 2 times the quantity x minus 4 squared for 3 less than or equal to x less than or equal to 6. And part A says that if f of 1 is 3, then what's the value of f of -5? We know from the fundamental theorem of calculus that if I ever want to find f of b, then I can just find what f of a is and add to it the integral from a to b of f prime of x dx. And that ends up being what I'm doing here. I know what f of 1 is, and I'm trying to find f of -5. And that means that I have to be doing the integral from a to b of my function, which in this case is g of x. But I see a couple of things that I'm going to have to watch out for. Number 1, my limits seem to be in the wrong direction. So I could say that this is equal to f of 1 minus the integral from -5 to 1 of g of x dx. And 2, because my function is piecewise linear on these intervals, it's going to be pretty easy for me to calculate this integral because it's just going to be equal to the area. So I've got this area from -5 to -2. That's a square with an area of 9, and it's below the x-axis, so it's negative. I've got this triangle with a base of 1 and a height of 3, so this is -1.5. From here to here, I'm constant 0. And then from here to here, this is going to be a triangle with a height of 1 and a height of 2 and a base of 1, so it's going to be an area of 1. So I'm going to have 3 minus this expression. It's going to be 1 minus 1.5 minus 9. Now, of course, I'm perfectly legit in leaving my answer this way. I could simplify this and just say that it's equal to 3 minus 1 plus 1.5 plus 9. It's 9 and 3 is 12. Take away 1 is 11. Take away 1.5, or add 1.5, and that's going to give me 12.5. But this is a perfectly fine answer because it's correct. And there's no reason to try and make that extra math happen if there's a chance you can get it wrong. All right, part B, we want to evaluate the integral from 1 to 6 of g of x. Notice that from 1 to 3, we've got a linear function, and this is going to be a square. But from 3 to 6, I've actually got this parabola, so we will have some math going on here. So I know that this is going to be equal to the integral from 1 to 3 of g of x dx, plus the integral from 3 to 6 of g of x dx. And this is going to be easy because this is just that square with the area of 4. Over here, I'm going to have the integral from 3 to 6 of 2 times x minus 4 squared dx. So I'm going to have to integrate this using the power rule, using the chain rule, but u in this case, u substitution, u is 1. So it's going to be 4 plus, this is going to be 2 times my expression cubed over 3, which I'm evaluating from x equals 3 to x equals 6. So it's going to be 4 plus this expression. I'm going to have 6 minus 4, which is 2 cubed times 2 over 3, minus, here I'm going to have 3 minus 4, which is -1 cubed times 2 over 3. And again, this is a perfectly acceptable answer. I could leave my answer in this form, and there's no reason for me to do any more math at this point. On part C, it says, for -5 less than x less than 6, on what open intervals, if any, is the graph of f both increasing and concave up? So keep in mind, if f is increasing, that means that I want f prime to be greater than 0. And if I'm concave up, then I want f double prime to be greater than 0. But this is a graph of g. So I want to know, where is g greater than 0 and where is g prime greater than 0. So in other words, g has to be above the x-axis and increasing. Well, I know it's above the x-axis from 0 onwards, but it's only increasing from 0 to 1 and from 4 to 6. So f is both increasing and concave up when g is above the x-axis and increasing, which is at the interval 0, 1 and 4, 6. So that's part C. On part D, it says find the x-coordinate of each point of inflection in the graph of f. Keep in mind that a point of inflection is where concavity changes. So I want to know where f's concavity changes. That means I want to know where g changes direction, either from increasing to decreasing or from decreasing to increasing. And I'm looking at this and I'm going from constant to increasing, so this is not going to be a point of inflection. Increasing to constant, so that's not going to be a point of inflection. Constant to increasing, no. Increasing to constant, no. Constant to decreasing, no. Decreasing to increasing, this is the only place where g actually changes direction. So I could say that x equals 4 is a point of inflection, or is the x-coordinate of a point of inflection, because it is the only position where g changes from increasing to decreasing, or vice versa. So the thing is, I have to give the answer, x equals 4, and I have to give my justification. I need to give a reason for my answer, and I need to justify it in terms of what I see in the graph of g. So that's problem 3. Taking a look at problem 4, we're given this table, and they tell us that the height of tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. And it says, use the data in the table to estimate h prime of 6 using correct units, interpret the meaning of h prime of 6 in the context of the problem. So h prime of 6, that is my instantaneous rate of change, but I know that I can approximate that by looking at the average rate of change, which would be the behavior on either side of 6. In other words, taking a look at what's happening at t equals 7 and what happens at t equals 5. So I can say that it's approximately equal to h of 7 minus h of 5 over 7 minus 5. So I can say that that's 11 minus 6 over 7 minus 5. And using correct units, keep in mind that we're talking about a change in meters over time. So this is meters per year. So in other words, I could say the tree is growing at approximately 11 minus 6 over 7 minus 5 meters per year at 6 years. So I've interpreted the meaning of this in the context of the problem. That's approximately the rate at which we're growing. On to part B. Part B says, explain why there must be at least one time t for 2 less than t less than 10, such that h prime of t is equal to 2. And one of the important parts here is the fact that they told us that h is twice differentiable, which means that h prime is differentiable, which also tells me that h prime is continuous. And this is going to be important because I'm going to be using the intermediate value theorem. In other words, if I can show that at some point h prime of t was greater than 2, and then later on h prime of t was less than 2, then I know that h had to reach 2 somewhere between t1 and t2. And so that's really what we're going to be going for. So I can say that if I take a look at this, I can take a look at what's happening on several of these intervals, from 2 to 3, 3 to 5, 5 to 7, and 7 to 10. And I know that I can approximate h prime of t by using that average rate of change. Now, it's not going to be enough to tell me that I know it has to be that, but it kind of gives me the gist that it has to be going from below a value of 2 to above a value of 2, and then I can imply with the continuity and intermediate value theorem. So I could say that h prime of 2.5 is approximately equal to 2 minus 1.5 over 3 minus 2. Well, this is 1/2 and this is 1, so this is 0.5. If I take a look at what's happening at h prime of 4, that's going to be approximately equal to 6 minus 2 over 5 minus 3, which is 2. So my approximate is approximately 2. And we know from the previous problem, h prime of 6 is going to be 11 minus 6 over 7 minus 5, which is 2.5. So I could say that since h prime of t changes value from a value less than 2 to a value greater than 2 by the intermediate value theorem, h prime of t must be equal to 2. So I know that I'm using the continuity, I'm using the intermediate value theorem, and I'm using the fact that I can estimate the instantaneous rate of change using the values in the table. And on to part C. Part C says, using a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 less than t less than 10. Remember that my average value of a function is going to be 1 over b minus a times the integral from a to b of my function with respect to time. So in this case, I'm going to be doing my average height is going to be 1 over 10 minus 2 times, and I'm going to have to approximate the integral by using a trapezoid. So for my first trapezoid, my height is going to be 3 minus 2, and my bases are going to be 2 plus 1.5 over 2. That's my first trapezoid. My second trapezoid is going to go from 3 to 5, with my heights going from 6 to 2. My third trapezoid is going to go from 5 to 7, and my heights are going from 11 down to 6. That's a plus. And then my next trapezoid is going to be 10 minus 7 times 15 plus 11 over 2. And so this is my average height of my tree, and keep in mind, because we are talking about units being given, I do need to say that this average height is in meters. So that's part C, and now on to part D. Part D says the height of a tree in meters can be modeled by the function g, given by g of x is equal to 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.3 meters per year. And it says, according to this model, what is the rate of change of the height of the tree with respect to time. Well, I'm looking for the rate of change of the tree with respect to time. The problem is this g is a function of x. So what I'm really looking for, that's going to be dg dt, has got to be equal to dg dx times dx dt. That's just the chain rule. And so I'm looking for the change in g with respect to x, which is going to be the derivative of this function, times the change in x with respect to t, which I know is 0.03. So my change in g with respect to t, and I'm going to have to evaluate this at, well, whatever the time is when my height is 50. So if my height is 50, then what I've got here is 50 equals 100x over 1 plus x. This is going to allow me to find out, okay, what is my height, or what is my radius at that time? So I'm going to have 50 minus 50x, or 50, ooh, ugly, 50 plus 50x equals 100x. So 100x minus 50x equals 50. And so 50 equals 50x. And so x equals 1 meter. Well, goodness, that makes things really nice. So I want to know what's happening when x equals 1, basically. So I'm evaluating dg dt when x equals 1. So I'm going to have to figure out what the derivative of g is with respect to x. I'm going to use the quotient rule, so the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And it's going to be all of that times dx dt, which is 0.03. And what's nice is x is equal to 1 is something that's really easy to plug in. So dg dt is going to be equal to 2 times 100 minus 100 over 1 plus 1 squared times 0.03. And that's going to be in terms of meters per year, because it's a change in height over time. And of course, nothing wrong with this. I can leave my answer in this form. If I wanted to simplify it, then I would just end up with 0.75? Whatever that calculates out to, but it would be a horrible mistake to actually try and calculate that out, especially in my head like I just did. All right, so that's problem 4. On to problem 5, we've got polar graphs here. The graph of the polar curves r equals 4 and r equals 3 plus 2 cosine theta are shown in the figure above. And they tell us that the curves intersect at pi over 3 and at 5 pi over 3. And they say let r be the shaded region that's inside the graph of r equals 4 and also outside the graph of r equals 3 plus 2 cosine theta as shown in the figure above. Write an expression involving an integral for the area of r. And I know that whenever we're dealing with polar area, I know that the area is going to be equal to the integral of 1/2 r squared d theta from theta 1 to theta 2. But because I'm dealing with two shapes, I'm going to have to take the outer area and subtract the inner area. So it's going to be equal to 1/2 my big R is the circle, which is 4, minus my small r, which is going to be the 3 plus 2 cosine theta. And I'm going to integrate that with respect to theta, and they told us the limits were pi over 3 and 5 pi over 3. So I've got a integral that expresses the area. The area of the outside circle, 1/2 r squared, minus the area of the outside of the cardioid, which is 1/2 3 plus 2 cosine squared theta. All right, part B. So on part B, it says find the slope of the line tangent to the graph of r equals 3 plus 2 cosine theta at theta equals pi over 2. So I know that y is equal to r sine theta and x is equal to r cosine theta. And the reason that I bring this up is that slope is supposed to be the change in y over the change in x, but that's really going to be dy d theta over dx d theta, because of the chain rule. So I need to take the derivative of r times the sine of theta. So I've got to take the derivative of r, 3 plus 2 cosine theta, times sine theta. And I've got to take that over the derivative of x, which is going to be r times cosine theta. And in order to calculate this, I'm going to have to use the product rule. So for the product rule, I'm going to have my first expression times the derivative of the second plus my second times the derivative of the first. And the derivative of this is going to be negative 2 sine theta. Over, here I'm going to have the first times the derivative of the second, which in our case is negative sine theta, plus the second, cosine theta, times the derivative of the first, which is going to be negative 2 sine theta. Now, they give us this theta equals pi over 2, so if I'm looking for my formula, this is my formula as a function of theta. So if I want to figure out the slope when theta equals pi over 2, then I want to substitute pi over 2 into this. Well, I know that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So everywhere I see cosine of pi over 2, that term's going to go away. And whenever I see sine of pi over 2, that term's going to be 1. So what I've got is I've got 3 plus 0 times 0 plus 1 times, in this case, negative 2 over 3 times 1, negative 1, because of this negative sign here, plus 0 times negative 2. And I certainly can leave it like that. I don't have to say that it's going to be equal to negative 2 over negative 3, or 2/3. But I can use this to justify what's going on. At pi over 2, my tangent line is a positive slope, but it is a shallow positive slope. It's not increasing very fast. It's actually increasing at less than a 1-to-1 rate. So I get that graphical confirmation of my answer. And on to part C. On part C, it says, a particle moves along the portion of the curve r equals 3 plus 2 cosine theta. For theta between 0 and pi over 2, the particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. In other words, the change in r with respect to time is going to be 3 units per second. And they want to find the rate at which the angle theta changes. In other words, we're trying to find d theta dt. Well, if I look at this from a standpoint, I know r is some function of theta, and I want to know the rate of change of theta with respect to t. So I could say, using the chain rule, that dr dt has got to be equal to dr d theta times d theta dt, and this is the quantity that I'm trying to find. I know that this is 3. And I can find the derivative of this because the derivative of a constant is 0, and the derivative of this is going to be negative sine. So I've got negative 2 sine theta times d theta dt. And I'm interested with what's happening at theta equals pi over 3. So I could say that d theta dt is going to be equal to 3 over negative 2 times the sine of pi over 3. And of course, this is a perfectly acceptable answer, except I do need to indicate units of measure, and I'm talking about how an angle changes. Remember that angles are measured in radians, and my time unit, they told us, was seconds. So this is going to be that many radians per second. So that's problem 5. Now we move on to problem 6. The Maclaurin series for natural log 1 plus x is given by this alternating series, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus etc. And it says on its interval of convergence, this converges to ln of 1 plus x. Let f be the function defined by this, x times ln of x plus x over 3 plus 1. And they want us to write the first 4 non-zero terms and the general term. So what's happening here? Everywhere that I see an x, I'm replacing with x over 3. So this is going to be x over 3 minus x over 3 squared over 2 plus x over 3 cubed over 3 plus x over 3 to the 4th over 4 plus dot dot dot. And this is still an alternating series. This is going to be x over 3 to the n over n. Now that's just the natural log of 1 plus x over 3. I still need to multiply that times x, so I need to multiply this whole thing times x. So that's going to give me x squared over 3 minus, this is going to be x times x times x, so x cubed over 3 squared times 2. This is going to be x to the 4th over 3 cubed times 3. This was a minus sign, thank you. Minus x to the 5th over 3 to the 4th times 4 plus dot dot dot. And this is going to be negative 1 to the n, x to the n plus 1 over 3 to the n times n. So that's going to be my expression. There are my first 4 non-zero terms. Of course, there's a 1 there that I didn't need to write, but it makes it easier to identify the pattern. And so that's part A. On part B, they're asking us to determine the interval of convergence, and probably the easiest thing to do would be to look at the ratio test. In other words, I want to know what's going to happen when I take the look at a sub n plus 1 over a sub n, the limit as n increases without bound. And of course, I really want to know when this is going to be less than 1, because if that's true, then that means my terms are getting smaller successively. So looking at this from our previous answer, f for us was, f of x was x to the n plus 1, negative 1 to the n plus 1 over 3 to the n times n. So our ratio test, we're looking for the limit as n increases without bound of negative 1 to the n plus 2, because I'm adding 1, times x to the n plus 2 over 3 to the n plus 1 times n plus 1. And this is all divided by, so I'm going to multiply by the reciprocal. I'm going to have negative 1 to the n plus 1, x to the n plus 1, over 3 to the n times n. And of course, because I've got the absolute values, these don't really matter. What matters is this value of x here and this value of x here. So I'm going to have x to the n plus 2 times 3 to the n times n over x to the n plus 1, 3 to the n plus 1 times n plus 1. And I'm looking to see what happens as n increases without bound, and I want this to be less than 1. In other words, I really want this, x over 3, because that's what happens. This limit, of course, is 1. I want to know where this is less than 1. So negative 1 is less than x over 3 is less than 1. So negative 3 is less than x is less than 3. Now I'm looking for the interval of convergence, so I am going to have to check my endpoints. I'm going to see what happens when x is negative 3, and I'm going to see what happens when x equals 3. If x is a negative 3, then I end up with negative 3 to the n plus 2 times 3 to the n times n over 3 to the n plus 1 times n plus 1 times negative 3 to the n plus 1. And so this is n plus 2 plus n, so this is really 2n plus 2 on the top, 2n plus 2 on the bottom, so all of these are going to cancel out, and it's just going to leave me with n over n plus 1 as n increases without bound. Well, this is equal to 1 always, so we do not have equality. And I can use the exact same argument just without minus signs here, but this is not going to be equality as well. When I take that limit as n increases without bound of positive 3 to the n plus 2 times 3 to the n times n over 3 to the n plus 1 times n plus 1 times 3 to the n plus 1. The same thing's going to happen. All of these 3's will divide out, leaving just n over n plus 1 equals 1. So this is, in fact, my true interval of convergence. And this is going to take us to part C. Part C says, let P sub 4 of x be the fourth degree Taylor polynomial for f about x equals 0, using the alternating series error bound to find an upper bound. Keep in mind that if I want to use the alternating series error bound, I need to know two things. One, are we an alternating series? Well, yeah, we are an alternating series because our series has that negative 1 to the n plus 1 part of its term. And two, if I take a look at a sub n plus 1, is a sub n plus 1 always going to be less than or equal to a sub n? And we saw that was happening when we did our ratio test earlier. So this satisfies everything we need for the alternating series test bound. And so I know that P4 of 2 minus f of 2 has got to be strictly less than or equal to my fifth term. So my fifth term is going to be that negative 1 to the 6th times x to the 6th over 3 to the 6th times 6. And I want to know what's happening when x equals 2. So I'm going to have, of course, negative 1 is going to go away because of the absolute value. So this is going to be 2 to the 6th over 3 to the 6th times 6. This is my error bound. And so that's it. That's what we're looking for. Overall, I thought the questions on this test were very approachable, despite what you saw on the internet about all the memes. Some of the questions, I guess, could be interpreted very funny, but otherwise I felt that all the aspects of the class were stuff that we've touched upon. Hope you did very well. Hope you enjoyed your class. Good luck on your next endeavors. Once again, this is Mr. Potter. Thank you for watching. Have a great day.